We are studying counting and probability, two extremely interesting concepts, and they are very much intertwined. To study the field of counting, we have to look at two very important principles. The first one, the first counting principle. So if we have 3 pants and 2 shirts, how many combinations can we make? In other words, how many different outfits can we make? So if we choose red pants, we have got 2 shirts to choose from. So, in other words, for each pair of pants, we have got 2 shirts to choose from. And that makes 6 combinations. 3 multiplied by 2. And that brings us to the first counting principle. If there are m ways of doing one thing and n things of doing another, after the first one has been done, then using no other restrictions, there are m times n ways of doing both together. So let's fill that in. M times by n. The second counting principle follows on this. If we have 2 skirts, 4 blouse options, and 2 sweater options, we can say that we can make 2 times 4 times 2, which equates to 16 different outfits. So, to generalize that, suppose we need to fill our boxes. If the first box can be filled in M1 ways, the second in M2 ways, the third in M3 ways, and so on, until the rth box, which can be filled in MR ways, then all our boxes can be filled in M1 times M2 times M3 all the way to MR ways. In this case, for the number of skirts, blouses, and sweaters, we can say that we have 2 times by 4 times by 2 different options. And this then, the first and second counting principle. Let's define probability. The probability of an event is a number that indicates how likely the event is to occur. It is expressed as a number in the range from 0 up to 1. So, probability is a number expressed in the range from 0 up to 1. The more likely it is that the event will occur, the higher its probability. The probability of an impossible event is 0, and that of an event that is certain to occur is equal to 1. Now, if we look at the throwing a die with 6 sides, what's the probability of throwing a 6? The probability of throwing a 6, in this case, will be 1 out of 6. How do we arrive at that? The numerator indicates the number of options in which we can throw a 6, which in this case is only one option, whereas the denominator is our sample space. That means all the different options. And in this case, there's 6 sides, so there are 6 different options. Here is just a fun question to demonstrate probability. Now, if I throw 2 dice, then how many outcomes do I have? If I use the first counting principle, and there's 6 ways of throwing the one die and 6 ways in throwing the second one. The total number of outcomes is 36 according to the first counting principle. And here you can clearly see that if the one die is a 1 and the other one is a 1, we get 1 and 1. And likewise, if the one die is a 1 and the second one a 2, we get 1 and 2. 36 different outcomes. So, in this fun question, if I roll 2 dice 10, what would you rather roll 2 dice 10 times, and which option will be more beneficial? So receive $5 every time you get a double, or receive $5 every time you get any two even numbers. So let's see, what's the probability of getting a double? A double is represented by this diagonal, and that is then 6 of the 36 options, which represents 1 over 6. So the probability of receiving $5 is 1 out of 6. What's the probability of receiving $5 every time you get any two even numbers? So let's circle those. Two even numbers. And we can see that that will definitely be a higher probability. And this time, this is 9 out of 36. 9 out of 36, which is a quarter. So option B is more beneficial. What happens if we ask the following question? The probability of throwing a double or two even numbers. Now from this comes a very interesting formula. So this bucket means or, which means the one or the other. It's not and. So if I look at that, the formula for this is the probability of throwing a double plus the probability of two even numbers. We've got those. But now, in this case, we have counted, as you can see, we have counted some of the options twice. Let's look at which ones. This has been counted twice. So, we have to subtract the probability of a double and. This upside down bucket means and, which means both are true at the same time, and two even numbers. So that results in, if I use this formula in blue, so let's say I'm going to say that this equals, let me just put an equal sign over there. So the probability of a double is 1 over 6. The probability of two even numbers is 1 over 4. But we have to subtract those that appear twice, which is 3 out of 36. You can see in the blue, 3 out of 36, which reduces to 1 over 12. And this then, if I have the same denominator, will result in, that will be 2 over 12 plus 3 over 12 minus 1 over 12, which is then 4 over 12, and 4 over 12 is a third. Here we have a very simple counting problem. In how many ways can 90 cents be made up of 10-cent coins, 20-cent coins, and 50-cent coins? So we've got 50-cent coins and 20-cent coins and 10-cent coins. Now we could possibly, in method 1, we could do it like this and say that 10 cents plus 10 cents 9 times make 90 cents. And quite a tedious exercise, and that will give us 90 cents. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's tedious. As mathematicians, we're always looking for a better method. So let's look at method 2. In method 2, we could say that X, let X represent the number of 50-cent coins. So it's the number of number of 50-cent coins, and then let Y represent the number of 20-cent coins and Z the number of 10-cent coins. So we know that we could simplify this or write this an equation. We're always looking for an equation in maths. 50x plus 20y plus 10z equate to 90. And that of course simplifies to 5 plus 2y plus z equals 9. Now, if we look at this, we know that there could either be let's start with no 50-cent coins or one 50-cent coin. These are the only scenarios, because if I've got no 50-cent coins, I could make up 90 cents with the 20 and 10-cent coins. If I've got one 50-cent coins, the remainder could be made up of 20 and 10-cent coins. But the minute I've got two 50-cent coins, that will be 100 cents, which is 1 rand more than the 90 cents required. So let's see what happens if x is 0. Mathematically, that will then be 2y plus z equals 9. So 2y is equal to 9 minus z. This means that this must be an even number because of the fact that there's a 2 in front of the y. So 9 minus z must be even. So if 9, that's odd, in order to get an even number, it means z must also be odd. So what are the options for z? Z could be 1, a 3, a 5, a 7, or a 9. It can't be greater than 9 because then I've got nothing left. So let's see if we have no 50-cent coins and we say that let's make z there's one 10-cent coin. One 10-cent coin which will result in 10 cents. If there's one 10-cent coin, that means that we'll have 9 minus 1z, which is 8. So 8 equals to 2y. That means there must be 4 20-cent coins. And 4 20-cent coins results in 80 cents, and it worked beautifully. If we look at the next option and we make z 3, 9 minus 3 is 6. So that will result in a 30 cents for three 10-cent coins. And then the remainder is 60. 60 to get how many 20-cent? So let's just say 20-cent coins that will be. So we've got, if I write that down, 2y is equal to 6, 9 minus 3. So y must equal to 3. So there are 3 20-cent coins, which results in 60, and it worked. And similarly, if we subtract 5, we have, that means that if we subtract 5, 9 minus 5 is 4, 4 10-cent coins, which is 40 cents. And that means that 9 minus 5 is 4, so y is equal to 2, 2 20-cent. Let me just see, I made that, okay, sorry, that's a 5, so that will be 5 10-cent coins is 50 cents, and then that means that there are 2 20-cent coins, which is then 40 cents. The next option is for z to equal to 7. That means that there's 7 10-cent coins, 70 cents. 9 minus 7 is 2, and 2y equals to 2. That means there is 1 20-cent coin, 1 20-cent coin. So, and then the last option is to make z equal to 9. If z equals to 9, then we will have, that will then result in 9 minus 9, which is 0, and that is then 90 cents. That will result in the 90 cents, 9 10-cent coins, and 0 20-cent coins. And it worked beautifully. That's our first scenario. Our second scenario is let x equal to 1. Now, if x is equal to 1, my equation from here will be 5 times by 1 plus 2y plus z equals to 9. So this time we get z is equal to 9 minus 5 is 4 minus 2y. And take out a common factor of 2, 2 minus y. So z is now equal to 2 times 2 minus y. Now, I know that this must be a positive. I can't have a negative number of coins. So y could be, so in my second scenario, where x equals to, let's say 1, x equals to 1, y could be a 0, a 1, or a 2. If y is 0, we have no 20-cent coins. So that will then be no 20-cent coins. And let's look at the equation. Z will then equal to, so we've got no 20-cent coins, so let's say 0. And let's look at the equation. Let's sub that in. 2 minus 0. So z equals to 4 because that will be a 0. So that means I've got 4 10-cent coins, which results in 40 cents. So I've got 150 cents. So let's change this to a 50 because I've got 150 cents. And that makes 90 cents. Let's make y 1. If y is 1, I get 2 minus 1 is 1. And that means I've got 2 z's. That's 2 10-cent coins, which is a 20, that will be 2 10-cent coins, 20 cents, one 20-cent coin for y is 1, and then the 50 cents, resulting in 90. Last option is that I have y equal to 2. That means z is equal to nothing. So that means no 10-cent coin, 2 20-cent coins is 40 cents, and then the 50 cents. So in how many ways can 90 cents be made up of 10-cent coins, 20-cent coins, and 50-cent coins? And we can count and see that there are 5 solutions when there are no 50-cent coins, and 3 solutions when there's 1 50-cent coin. All in all, resulting in an answer of 8 ways. So we did this. It took quite some time to demonstrate the algebra, but once you understand it, it's actually very quick, instead of using the tedious method of listing and maybe missing an option. Another counting problem. Some balls were distributed into each of 219 boxes, which were arranged in a row as indicated below. Any 4 consecutive boxes always had a total of 30 balls. How many balls were there in the 2019th box? Now let's say that there's X balls in the first box. And then let's make this Y balls. So we know that any 4 consecutive boxes equal to 20. That means the first 4 boxes, x plus 5 equal to 30, x plus 5 plus 7 plus y equals to 30. So that means that y equals to 30 minus x minus 12, which is equal to 18 minus x. So this y becomes 18 minus x. Now we've established the first 4 boxes. If I look at box 2, 3, 4 and 5, so let's make this box 5. I know that these boxes, let's have a look, these boxes 5 plus 7 plus 18 minus x plus this box must equal to 30. Therefore, this box is equal to x once again. Let's just have a look. 5 plus 7 plus 18 minus x plus x will equal to 30. Now we see that the pattern repeats. So in the next box, if I look at these 4, I look at 7yx. Y is 18 minus x. So let's write that down. 7 plus 18 minus x plus x plus, let's say, the number in box 6 must equal to 30. And we can see that 7 plus 18 will give us 25. So the number of balls in box 6 must be 5 once again. And the pattern continues like this: x, 5, 7, etc. So the pattern is a pattern of 4, x, 5, 7, 18 minus x, and the pattern repeats again: x, 5, 7, 18 minus x. So in every 4th box, I will have 18 minus x balls. Every 4th box. So let's establish. If I take 2019, we divide that by, let's divide that by 4. We will find that that is 504. 4 times 4 is 16, and a remainder of 3. So this will happen 504 times, and 504 times by 4 will get us to the 2016th box. Then in that box there will be 18 minus x balls. In the next box, as the pattern repeats in 4, there will be x balls, and that's in the 2017th box. In the 2018th box, there will be 5 balls, and in the 2018th box, and then in the 2019th box, as the pattern repeats in 4, there will be 7 balls. So the answer to this question is 7 balls. Before we continue with more questions, we are going to look at 2 very important concepts: permutations and combinations. Our question is, in how many ways can a red, green and blue ball be arranged? Most important here is that order matters. Now you can see that the arrangements have been done for us, and it is 6 arrangements in total. So we can use the counting principle to answer this question. For the first position, we've got 3 balls to choose from, then only 2, and then only 1. So we multiply these together and we find an answer of 6. 6 arrangements. In how many ways can 5 objects A, B, C, D, E be arranged? And that will then be 5 times by 4 times by 3 times by 2 times by 1. And that is 120 arrangements. How many 3-letter arrangements can be made from the 5 letters A, B, C, D, E? Now in this case, we are not using all the letters. So for the first position, we've got 5 letters to choose from, then 4, then 3, giving us 60 arrangements. And that then permutations where order matters. With combinations, order does not matter. If we look at these three balls, red, green and blue, that represents one combination. Whether we rearrange them or not, it is still the same combination and it counts as one combination. Should we exchange the blue ball for a black ball, that will be a new combination, yes. So, in how many ways can 3 letters be selected from the 5 letters A, B, C, D and E? Let's say we choose the letters A, B, C. And that now represents a combination. So, this represents one combination. If I permutate them and I find the number of permutations, that will be A, B, C, A, C, B, B, A, C, B, C, A, and lastly C, A, B, C, B, A. So that for this one combination, we have 6 arrangements or permutations. So, if we want to find the number of combinations, we will say the exact same thing that we did before. 5 times for position 1, 4 for position 2, 3 for position 3. So 5 times 4 times 3. But in order to lose the number of arrangements, we divide by the number of arrangements, and that will then be the number of arrangements is 6. 3 for the first position, 2 for the second position, and 1 for the third position, resulting in 10 different combinations. So now how many ways can 3 objects be selected from 5? We write this as 5, choose 3. So order does not matter, or 5, choose 3. This last notation is widely used in mathematics. What does it mean? We want to choose 3 objects. So we start from 5 for the first position, 4 times by 3. And then because of the fact that it's combinations and order does not matter, so we have to lose the number of arrangements. We divide through by the number of arrangements, which is 3 times 2 times 1. So that is then the same answer of 10. Now, let's say in how many ways can 5 lotto numbers be selected from 48 numbers? So 48, choose 5. So at the top we will write 48 for the first position, then 47 times by 46, 45, 44. That's the number of arrangements of 5 lotto numbers. But now we have to divide through by the number of arrangements of the 5 numbers. So how will we do that? Divide through, and the number of arrangements will be 5 times by 4 times by 3 times by 2 times by 1. And we can calculate that. Now, just to conclude on the notation of permutations and combinations, when we say 5 times by 4 times by 3 times by 2 times by 1, we can write that in short as 5 factorial. And that then is that means that's the number of ways in which we can permutate or arrange 5 objects. So let's have a look at 5 permutate 3 versus 5 choose 3. So 5 permutate 3, we've already looked at that. We said that will simply be 5 times 4 times 3. In factorial notation, we write that as 5 factorial over 5 minus the 3 factorial. And that is then 5 factorial over 5 minus 3, 2 factorial, which will result in the exact same thing. Why? 5 times 4 times 3 times 2 times 1, and that then divided by 2 times 1, and we get the exact same thing. Now, if I look at combinations, 5 choose 3, we already know that we write that as 5 times 4 times by 3, and then we divide that by the number of arrangements in order to lose the arrangements, and that will then be 3 times 2 times by 1. Now, to write this in factorial notation, we do the following. So we write this as 5 factorial at the top, and then the same thing, 5 minus 3 factorial, exact same thing as with permutations, but because of the fact that we want to lose the arrangement of 3 objects, we also divide through by 3 factorial, and that will give us 5 times by 4 times by 3 times by 2 times by 1, and then divide through by the 2 factorial over here, 2 times 1, and then also to lose the arrangements, 3 times 2 times by 1. So this will cancel, and then I will get the exact same answer, 60 divided by 6. So this factorial notation is looks like an exclamation mark, and is just the mathematical notation. Also important, note that we can generalize this as n permutate r, and that will then be n factorial over n minus r factorial, or n choose r, where arrangements, a number of arrangements does not matter, and we've got n factorial over n minus r factorial, r factorial. Very interesting. A last thing that I want to just say here is that n factorial can also be written as n times by n minus 1 factorial. Now, this is a whole topic on its own, but I'm just going to show you how we can link the choose function to binomial coefficients. Now, what does binomial coefficients mean? If I write down a binomial is a two-term, x plus y to the power of 0, that will simply be 1. When I write down x plus y to the power of 1, that's simply x plus y. X plus y to the power of 2. So this is row 0, row 1, row 2. So to the power of 2 and on row 2 is x squared plus 2xy plus y squared. What about x plus y to the power of 3 in row 3? So x plus y to the power of 3 will equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. Now, of course, you would have expanded this and multiplied it and got the exact same answer. But note that these coefficients of x and y correspond to this very interesting triangle, which is called Pascal's triangle. Why is it so interesting? I start with 1 at the top, then 2 ones. I add the 2 ones to get a 2 in the middle. Then I add these two, so I add each two adjacent numbers to get the number in the middle. 2 plus 1 gives us 3. And this triangle carries on like this with many other beautiful properties. For instance, here we've got the natural numbers. Here we've got triangular numbers, plus 2, plus 3, plus 4, plus 5. More about that just now. So, in this triangle, we can now see that this triangle has the exact same coefficients for the expansion of a binomial. So, for x plus y to the power of 1, I've got 1x and 1y. For x plus y to the power of 2, 1x squared, 2xy, and then y squared, also 1. With to the power of 3, 1, 3, 3, 1. Beautiful mathematics. So we can use these values in Pascal's triangle to do the expansion of a binomial. But the interesting thing is that if we use the choose function that we just had in the previous slides, these values correspond to these binomial, we call them binomial coefficients. So let's look at, if we say 4 choose 0. 4 choose 0 will be, as we know, 4 factorial over 0 factorial times by 4 minus 0 factorial, which is 4 factorial. And that is simply a 1. 4 choose 1, the next one. 4 factorial over 1 factorial. 4 minus 1 is 3 factorial, which results in a 4. What about 4 choose 2? 4 factorial. 4 minus 2 is 2 factorial, 2 factorial. And that will result in a 6. 4 choose 3. This one will be 4 factorial. 4 minus 3 is 1 factorial. And then 3 factorial. And that's once again a 4. 4 choose 4. The last one is 4 factorial over 4 factorial, 0 factorial. Note that 0 factorial equals to 1. So this, we are barely touching this very interesting topic, but just to show you how these the choose function relates to Pascal's triangle, and we call them the binomial coefficients, because of the fact that if we expand, or if we use these this, you can see 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. We'll get the coefficients of the expansion of x plus y to the power of 4, which is the exact same values as in row 4 of Pascal's famous triangle. So in the next row, if I have 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. We will get the entries for this row number 5. For row number 5 in Pascal's triangle, which will then also be the coefficients of the binomial, this binomial to the power of 5. If I expand that, I will find, so these values will correspond to these entries in row 5, and the coefficients of this expansion will also correspond to the entries in row 5. Just something very interesting to note. Now, another very interesting link is the link to the triangular numbers. If we look at these numbers, 1 plus 2 is 3, plus 3 makes 6, plus 4 makes 10, and we can carry on like that. Now, if we look at n plus 1, choose 2, that will result in, as we know, n plus 1 times by n, and then we divide that by the number of arrangements, which is then 2 factorial. So that will be divided by 2 times 1. Now, if I'm looking at let's say I'm looking at, so this is the first triangular number 1, number 2, number 3, here n is 4. Let's say we want to find the fifth triangular number. We will say 5 plus 1 is 6 times by 5, and that then divided by 2, which is 15. And wow, if I add 5 to 10, the next triangular number, we will find 15. So this is a way of finding the triangular numbers. We could also say that if I've got n choose 2, that will then be, if I've got n choose 2, that will then be n times by n minus 1 divided by 2. So this is another way of generalizing when I need to choose 2 objects from n objects. So just 2 very interesting links to the choose function. Let's look at this grid. Our aim is to find the number of paths from A to B. So let's suppose that this grid has B rows, and A columns. Now, we're only allowed to go up or to the right. And each path will define a unique code that consists of R's and U's. So let's say we've got a code here, R. So we can double check 1, 2, 3, 4, 5, 6, 7, 8. So we've got, that means our code will consist of 12 entries. Let's say R, and of which at least 8 of them must be R. So let's say we go up again, right, and another up. That means in order to get to the finishing point, we need 8 R's. So let's say R, 4 ups, and that then finishes our code of 12 entries. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At this point, we see that we have A plus B entries, and that it essentially mathematically corresponds to in how many ways can I choose A columns from A plus B entries, or alternatively, how many ways can I choose B rows from A plus B entries. And these two values will be exactly the same. Why? At the top we'll get A plus B factorial, and at the bottom here we'll have A factorial and A plus B minus A factorial, and exactly the same thing this side. A plus B factorial over B factorial, and then A plus B minus B factorial. And that, as you can see, is the exact same thing. So what does it correspond to in this case? 12, choose 4, or let me first say 8, because we've got 8 columns. 12, choose 8 corresponds to 12, choose 4, And that answer is 495 different paths. That would have been very difficult to count did we not have this powerful way of using the binomial coefficients. Let's look at another method which corresponds to Pascal's triangle. So we have the same grid again, and we want to find the number of paths. Now I can start off by saying that the number of ways to get to this point is simply one, same here, and all of these correspond to a 1 because it's just a straightforward horizontal path. Similarly, these entries also correspond to 1, but that means that to get to this point over here, there are 2 ways to get here. That will be either up and then right, or right and then up. Those are the 2 ways. And we can continue counting. And we'll notice that at this point, we'll have 3 ways. At this point, 4 ways, and at this point, 5 ways. And here over here, once again, 3, and here a 4, here a 6, and here we will have 10 and 15. How do I know this so quickly? You'll see that there's something very interesting emerging from this, and that is that if I look at this, 1 plus the numbers joining the 2 sides at this particular vertex is 1 and 1, we added, we get a 2. Here we've got a 3. We've got a 1 joining the 2, which will result in adding them, which gives a 3. Here we've got a 3 and a 1 resulting in a 4. So if we look at this particular entry over here, we will have a 6 and a 4, which will result in a 10. And we can carry on this way and see and finish this. And this is a little bit of a tedious exercise, but I'll have a 15 here again, and a 20, and here I'll have 35, and let's continue. Here will be a 35 again. Is that wrong? 20 plus 15 will be a 35 again, and we'll continue this way. And which entries are we still missing here? A 6, a 21, a 7, an 8, a 9. So I'm just simply adding. So what is this entry over here? Will be 21 plus the 7, which is 28. And we carry on this way. This is a 56. And I'll just add them quickly. 210. 330. I've now done this beforehand, so I know what these answers are. 84. And we continue adding this way. So I've got a 36 over here, and 36 and 9 is a 45. Here I've got 84 plus 36, which will give me 120. And then here we've got 165. Now if I add 165 to 330, I get to 495. Wow, that's the same answer we got with our previous method. But let's do a little bit of a further investigation. You'll see that these diagonals, if I draw a diagonal, let me take a different color. If I draw a diagonal like this, you'll see that this results in a Pascal's triangle that has been turned sideways. So here we can see the 1, 4, 6, 4, 1. And here we've got the 5, 10. So you can clearly see that this results in a Pascal's triangle. We also know that the binomial coefficients has a clear link to Pascal's triangle. How can we tie all of this together to find the number of paths? So if we look at each individual entry, let's say we're looking at this specific 10 over there. We can see that that is in column 3. Column 3, if I take 1, 2, 3, and that is row 2. Let's add that, 3 plus 2, and then if we say that entry corresponds to row number 2, that will give us 5 and a 2, which is 5 factorial, 2 factorial times by 3 factorial. And we know that that answer will then be, if I take that answer, will be 10. And we can find each one of these in a similar way. So if I look at this particular position, I can see that is 8 plus 4, 8 columns, 4 rows, and we are at the 4th row, and we already know that that answer is 495. So we get the exact same thing by using Pascal's triangle and the binomial coefficients. So to conclude, why does this work so well? First of all, we can see that, let's take this entry over here. We can see there's 6 ways to get to this point and 4 ways to get to this point. So if I add them 6 plus 4, it results in the 10. Why is it linked to Pascal's triangle? The reason for that is that's the exact same way Pascal's triangle works. It adds the 2 entries above together to find the entry in the middle between these two, 6 and 4, in the next row. So that is why this analogy works so beautiful. Now that we know all of this, we can tackle this problem. So this diagram shows a rectangular network of paths. How many ways are there to move from point A to point B if we can only move up or right without moving through intersection C? Now we know from our previous work that at this point we have one path and one path, and we add, and we know that this will result in Pascal's triangle's binomial coefficients. But we can simply add these paths. We add bottom to the side one to give us a 5. And here we'll find a 3, a 4, a 5. And 3 and 3 will result in a 6. Now all we need to do is to avoid point C. So let me just write the 6 a little bit clearer. So we need to avoid that point where there is a 6. So in this case, there will still be 5 paths because we are avoiding point C. Here we've got a 10, and then at this point still a 10 because we avoided point C, and then a 15 over here, and 15 over there, and here we've got a 10 plus the 15 will result in 25, add the 15, and a total number of 40 paths. Here is another problem where we simply have to use common sense. Fred puts 11 plastic bags inside another plastic bag. Each of the 11 bags is either empty or it contains another 11 bags. Altogether, 6 bags contain other bags. Of all the bags, how many remain empty? So we know that there's 11 plastic bags inside another plastic bag. Each of the 11 bags is either empty or it contains another 11 bags. Altogether, that's the magic word here. 6 bags contain other bags. So if I look at this, we see that of the 6 bags, the large bag with all the bags inside, with the 11 bags inside, that large bag contains bags. Large bag contains bags. So that means there's only 5 bags remaining with other bags inside. Bags remaining. So if we simply draw that, we say we've got a big plastic bag and inside we put 11 bags. Right, so that will give us 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we read it, Fred puts 11 plastic bags inside another plastic bag. We've drawn exactly that. Each of the 11 bags is either empty or it contains another 11 bags. Now, because we know that this outside bag already contains bags, there's only 5 bags remaining with 11 bags inside. 1, 2, 3, 4, 5. So how many of the bags will remain empty? Let's count. 1, 2, 3, 4, 5, 6. And then all of these 11 bags inside are also empty. So it's 5 times 11 plus the 6 that we just counted, resulting in 61. Here is quite an easy problem. The following sequence is composed of consecutive perfect squares. So we can see the first perfect square is 25, 5 squared, 6 squared, 7 squared, 8 squared, and then 9 squared. That will result in 10 of the 43 digits. 10 digits. 5 times by 2. Now the next square number is a 3-digit, which is 100, 10 squared. So that is 10 squared. So up to here, we've got 10 digits of the 43. So we still need 33 digits. We need another 33 digits. That could be composed of 11 3-digit square numbers. So all we need to do is see if we can find 11 3-digit square numbers. So the next one will be 11 squared, 12 squared, 13 squared, 14 squared, 15 squared, 16 squared, 17 squared, 18 squared, 19 squared, and 20 squared. Let's count. That will now be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So at the end of the 11th 3-digit square number, we will have an extra 33 digits. So we need that 11th 3-digit square number, which is 20 squared, resulting in 20 times by 20, which is 400. So the 43rd digit will therefore be a 0. The 43rd digit will be a 0. In each question, we are trying to find the easiest way to simplify the counting problem. So if I look at this question, we have a 3-digit number in which the hundredths digit must be smaller than the units digit. Now, if we look at that scenario, that means that the hundredths digit could not be a 9, else it's impossible for the units digit to be bigger. So this could be an 8, and this could be 7, 6, 5, 4, 3, 2, 1. So if the hundredths digit is a 1, the units digit could be a 2, 3, 4, 5, 6, 7, 8, 9 in order to be bigger. And we move up like that, and every time it becomes easier or one less digit, that will make the units digit bigger. So when the hundreds digit is a 3, the units digit could be a 4, 5, 6, 7, 8 or 9. If it's a 4, it could be a 5, 6, 7, 8 or 9. 5, 6, 7, 8 or 9. When the hundreds is a 6, it's simply 7, 8 and 9, and it becomes, the choices become limited now. Only an 8 and a 9, and when the hundreds digit is an 8, the units digit could only be a 9. Now, how many numbers? In the middle, we've got an option of 10 digits, and the middle digit could be any of these 10 digits, resulting in 10 numbers. If the hundreds digit's an 8 and the units digit a 9. And then 20 numbers, because now we've got a choice between 8 and 9, 30, 40, 50, 60, 70, 80. And we have to add this. And the cool trick to add, 10 plus 80 is 90, 20 plus 70 is 90, and 30 plus 60 makes 90, and 40 and 50 is 90. That results in 4 times by 90, and that is then 360 numbers in total. Here is an interesting year problem which involves the understanding of leap years. In 2014, August had 5 Fridays, 5 Saturdays and 5 Sundays. How will that be possible? Now that is only possible if we use the 28 days and then there's 3 days left. Within these 28 days, I'll have 4 of each day of the week. That means then to have 5 Fridays, 5 Saturdays and 5 Sundays, the 29th, 30th and 31st must be Friday, Saturday, Sunday. Now we know that there are 365 days in a normal year, and 52 times by 7 gives us 364 days. So in each year there is one extra day. But in a leap year, there's 2 extra days. There are 2 extra days in a leap year. Because in a leap year, we have the 29th of Feb, which results in 366 days. How do we know that a year is a leap year? It's easy because we just look at the last 2 digits. If the last 2 digits are divisible by 4, then the year will be a leap year. Divisible by 4, divisible by 4. So these are the leap years. So let's just list a few of them. 28 is divisible by 4 and then 32. So in a normal year, so this will then be, let's have a look in what happens in 2015. In 2015, the 29th of August, the 29th of August will be a Saturday because of the fact that we've got 1 extra day in each year, we move 1. So Saturday, Sunday, Monday. And then in 2016, because it's a leap year, I'll skip 2 days. So it won't be 29th of August won't be a Sunday, it will be a Monday. Skip Sunday. So we can continue like this. And then 2017 will be a Tuesday, the 29th. 2018, still not a leap year, we'll skip 1 day, a Wednesday. so that's 2018. 2019 will be a Thursday on the 29th. And then on the 2020 is a leap year again. So I'll skip 2 days, skip the Friday, and then get to Thursday, Friday. That will then be a Saturday. 2021. Skip a day, so that will be a Sunday. 2022 will be the 29th, will be a Monday. 2023, that will be a Tuesday. And then in 2024 is once again a leap year, so we skip a day, skip the Wednesday, this will be a Thursday. And then in 2025, the 29th will be a Friday again, resulting in the 30th a Saturday and the 31st a Sunday. Once again, because of the fact that we've got 28 other days where there will be 4 days of each weekday, in 2025 we'll have 5 Fridays, 5 Saturdays and 5 Sundays. So the answer to this question is in 2025. In this problem, we are going to use the counting principles. So we know that we have, in this case, we have an n-sided polygon. In this case, it's a 30-sided polygon. Let's first look at an n-sided polygon. So we want to know how many diagonals. So if we look at any vertex, we cannot construct a diagonal to the vertex adjacent to this current vertex. So this is our current vertex. So we cannot construct a diagonal to this one, neither to this one, neither to those two vertices. So, and we cannot construct a diagonal to the current vertex, in other words, this vertex that we currently counting diagonals. So that means that we have for the first position, we've got n vertices. We can only construct n minus 3 diagonals. Leave this one, leave that one, and leave that one. That's the counting principle. But because of the fact that if we count, let's say for instance, let's say we count this diagonal over here. And we're now counting diagonals from this point. We've already counted this diagonal. So in other words, we cannot count it again. Therefore, we must divide by 2. Now, if we apply this in a 30-sided polygon, will be 30 times by 27, and then divide that by 2, which will then give us 405 diagonals. Quite a nice problem. 3 randomly chosen faces of a cube are painted red. What's the probability that there are at least 2 adjacent red faces? So let's assume that we paint this side over here, we paint this side red. Now, to avoid painting adjacent faces red, we are going to paint the back side over here red as well. Now we still have to paint the third side. Now, whichever side we choose, at the back, on top here, or at the bottom, will be adjacent to one of the 2 sides that we've painted red initially. In other words, this side and that side. So what's the probability that there are at least 2 adjacent red faces? Will be 1. So that probability of at least 2 adjacent red faces will equal to 1. Here is quite a difficult counting problem. A die is rolled 6 times. What's the probability of rolling a 5 or a 6 at least 5 times? So if we've got more than one method, so let's look at method 1. This represents the 6 rolls. We have a sample space of numbers 1, 2, 3, 4, 5 and 6. In scenario 1, all boxes consist of 5s or 6s, all of them. So that means for each one of these rolls, we've got 2 options, and that is to the power of 6. But what if only 5? So all of them. If only 5 of the boxes, 5 rolls is a 5 or a 6, then we have 2 numbers to choose from, 5 times, and then we've got 4 numbers to choose from, these 4. So 4 numbers to choose from, but those 4 numbers can be in any of the 6 positions. So that gives us a total where we add these 2 totals, and let's add that. That will be 2 to the power of 6 plus 2 to the power of 5 times by 24, 4 times 6. Now, if I put that on the same denominator, let's see if we can do that. We can take out 2 to the power of 5 as a common factor, and we're left with 2 plus 24, which is 2 to the power of 5 times by 26. Now we want to know what is the probability. In order to get the probability, we have to divide this number by the total number of possibilities, and that will be 6 numbers to choose from for every single throw. So that's 6 to the power of 6. How will I simplify this without a calculator? Let's see. 2 to the power of 5 times by 26, and we prime factorize 2 to the power of 6, 3 to the power of 6. That looks much simpler already. And we can cancel this, and a 13 will remain over here, and that will then give us 13, and 3 to the power of 6 is easy to find, 729. Now that's method 1. Method 1. What about method 2? So we'll take the same approach for the, so let's say this is scenario 1 and scenario 2. So for scenario 1, where all boxes consist, or all throws consist of a 5 or a 6, the probability of rolling a 5 or a 6 is 1 out of 3. Or let's say in brackets 2 out of 6, because it's 2 numbers from 6. So that's 1 out of 3. If all of them consist of either a 5 or a 6, it's a third to the power of 6. But what about scenario 2? Here we've got 5 of the 6 throws produce a 5 or a 6. Now that means that the other throw, the throw that is not a 5 or a 6, for that possibility is 4 out of 6, which is 2/3. But once again, we know that this 2/3 probability could have fallen in any of the 6 slots. So that gives us times by 6. But then we must remember we must multiply this by the third to the power of 5 for the 5 throws that represent a 5 or a 6. So this, let me just take out this equal sign. So this is then my probability for throwing 5, where 5 of the 6 throws produces a 5 or a 6. And we simply add this. So let's add this, and we get a third to the power of 6 plus 2/3 times by 6 times by a third to the power of 5. How can we simplify this? Let's have a look. We could take out, we've got a third here as well, so we could take out a third to the power of 6, which will result in 1 plus 2 times by 6. And that gives us once again the same answer, 13/729. Here is quite a tedious problem. Let's look at two different methods, where the first one's quite a bit of work. So method 1, and we want to find how many numbers between 100 and 999 have their digits in strictly increasing order. Now, in increasing order, note that 459 is strictly increasing, but 455 is not, because the two 5s are the same. Now, let's say we start off with the first digit being a 1. Let's say the second digit is a 2. Then the third digit could be a 3, a 4, a 5, a 6, a 7, a 8, or a 9, resulting in 7 numbers. But then, if the second digit was a 3, we'll only have 6 numbers, because then the third digit must be 4, 5, 6, 7, 8, or 9. And we carry on that way. This is a 4, a 5, a 6, a 7, or a 8. And that's the only options that we've got. Then this could be 5 numbers, 4, 3, 2, 1. And we add all of that, and that will give us 8 times 3 plus 4 is 28 options. Likewise, if the first digit is a 2, then the second digit could only be a 3, a 4, a 5, a 6, a 7, or an 8. And likewise, then we'll get 6 numbers, 5 numbers, 4, 3, 2, 1. And if I add that, that will be 7 times 3, which is 21. And we can continue in this way. So let's say the first digit is a 3. Then the second digit could be 4, 5, 6, 7, or an 8. And likewise, like we've discovered, there's then 5 options for the third digit, 4, 3, 2, 1, resulting in 5 plus 4, that will be 6 times 2 plus 3 is 15. You'll note that these are actually the triangular numbers in reversed order. So what we'll have is 28 minus 7 is 21, minus 6 is 15, minus 5 is 10, and then minus 4 is 6, plus 3 plus 1. Which scenario is 1? That is when the first digit is a 7. A 7, and then we only have one number, which will be 789. So if we add all of these triangular numbers, we find a total for these triangular numbers of 84 numbers. Now method 2 requires fancy mathematics, but it's much easier. So what we're looking at is if the first digit is a 1, a 2, a 3, a 4, a 5, a 6, or a 7. We have to choose 2 digits. In this case, we will choose 2 digits from 8 digits. Here, we'll choose 2 digits from 7 digits. Choose 2 from 6, choose 2 from 5 remaining, choose 2 from 4, choose 2 from 3, and choose 2 from 2. And that will give us, if we look at the formula, which we know now, 8 choose 2, alternative way of writing this, is equal to 8 factorial over 2 factorial over 6 factorial, and if we calculate that, that will give us, we will have 8 times by 7 left divided by 2 is 28, and we'll get the exact same answers than we did before. How beautiful is this mathematics? And that will result in the same answer of 84 numbers. During a survey in a small town, it was found that in a family with 3 children, at least one child was a girl. The probability that at least 2 of the children were girls is x over 65. Assuming that the probability of having a girl is equal to the probability of having a boy, find the value of x. Now we know that the different options here will be boy, boy, boy. If we do it systematically, boy, boy, girl, boy, girl, boy, and boy, girl, girl. Then 3 girls, girl, girl, boy, girl, boy, girl, and girl, boy, boy. Now, it is found that in a family with 3 children, at least one child was a girl. So it's given to us that at least one child was a girl. And in this case, we're looking at only the following options. So these are the only ones that we are considering as it was given to us. Now the probability that at least 2 of the children were girls is x out of 65. That means that we are considering only 7 cases. And out of these 7 cases, 4 of the 7, let's look at which 4. 2 girls, 2 girls, 2 girls, and here we have 2 girls. So we have 4 out of the 7 cases. 1, 2, 3, 4 out of the 7 cases. We have 2 girls. And we know that that probability is x out of 56. So that is then easy to find by cross multiplying. 4 times by 56 equals to 7x, and we can say 4 times by 8 equals to x when we divide by 7. Therefore, x equals to 32. So this then means that the probability that at least 2 of the children were girls is equal to 32 out of 56.